Hello students, welcome to EPG Pathshala. I am Dr. Savita Sharma from University of Delhi. Today we are going to talk on the module X-ray diffraction part 2 under the paper Thin Film Science and Technology. So students, let us see what we are going to learn in this module. First of all, you are going to learn about the diffraction directions. The next, you will learn about the intensities of diffracted beams. Then we will derive and study in detail about the structure factor of body-centered cubic and face-centered cubic lattices. Then we'll study about the experimental X-ray diffraction patterns, in which we'll study mainly the three methods: Loewe method, rotating crystal method, and powder method. So before going into detail, let's have a brief introduction. In the previous module, diffraction of X-rays by crystal is explained. We have already studied that diffraction can occur only when Bragg's law is satisfied. The directions of diffraction of X-ray beam from a crystal are determined, and the factors governing the intensity of diffraction beams are discussed. Also, Bragg's equation applies conditions on lambda and theta for any given crystal. With monochromatic radiation, a single crystal will not produce diffracted beams for arbitrary angle of incidence of X-rays onto the crystal. In order to satisfy Bragg's law, it is necessary to scan in either wavelength or angle to satisfy diffraction conditions. Experimentally, it is done by providing a continuous range of values of either lambda or theta during an experiment. Thus, in this module, the various experimental methods of X-ray diffraction are studied. Diffraction directions. In order to determine the possible directions, that is, possible angles to theta in which a given crystal can diffract a monochromatic beam of X-rays. For that, a general relation is required which can predict the diffraction angle for any set of planes. This relation can be obtained by combining Bragg's law and the interplanar spacing equation for the particular crystal under study. For example, consider a cubic crystal. The interplanar spacing d for particular HK L planes is related to the Miller indices HK and L and lattice constant A, where relation 1 by d square is equal to h square plus k square plus L square divided by A square. Now combining with Bragg's law, which is lambda is equals to 2d into sine theta, we can put the value of d from this and we can obtain the above equation as sine theta whole square equals to lambda square divided by 4a square into h square plus k square plus L square. This equation predicts all possible Bragg angles at which diffraction can occur from the planes HKL for the particular incident wavelength lambda and a particular cubic crystal of unit size A. For example, for 110 planes, the above equation can be written as sine theta whole square equals to lambda square divided by 2a square. Here we have put the or substituted the values of h, k and L to be 1, 1 and 0. For a tetragonal crystal having the axes as A and C, the corresponding general equation is sine theta whole square equals to lambda square divided by 4 into h square plus k square divided by a square plus L square by C square. Similarly, the equations can be obtained for other crystal systems. Thus, it can be inferred that the directions in which a beam of given wavelength is diffracted by a set of lattice planes is determined by the crystal system to which the crystal belongs and its lattice parameters. That is, diffraction directions depend solely on the shape and size of unit cell. Conversely, the above point can be stated as all that can be determined about an unknown crystal by measurements of the directions of diffracted beams are the shape and size of its unit cell. Now let us study about the intensities of diffracted beams. We have seen that the directions in which diffraction occurs according to Bragg's law is governed entirely by the geometry and size of unit cell. These directions are completely independent of the arrangement of atoms associated with each lattice point, which is called as bases. However, the constitution of the atomic structure within the unit cell affects the intensity of diffracted beams. The intensity of the diffracted beams primarily depends on the atomic scattering factor and the position of each atom within the unit cell. Since the electrons are the only components of the atom that scatter X-rays significantly, therefore, the X-rays scattered from one part of the atom interfere with those scattered from the other parts at the all angles of scattering. As the electrons are distributed throughout the atomic volume, the diffracted beams are obtained as a result of combination of scattered waves from the electrons of all the atoms in a unit cell. This process involves two distinct contributions. Number one, scattering of electrons in the same atom, which is called as atomic scattering factor or atomic form factor. Secondly, the summation of the scattering from all the atoms in the unit cell, which is called as a geometrical structure factor, or which is represented by capital F or S. The atomic scattering factor is a measure of the efficiency of an atom in scattering X-rays. It is defined as the ratio of the amplitude scattered by actual electron distribution in an atom to that scattered by one electron localized at a point. Therefore, if the atoms are assumed to be points only, then the atomic scattering factor is just equal to the number of electrons present, that is, atomic number of neutral atom Z. The atomic scattering factor of an atom falls off with increasing value of sin theta by lambda. In order to find out the intensity of X-ray beam scattered by one unit cell in a particular direction where there is diffraction maximum, it is necessary to sum the waves that arise from all atoms in the unit cell. That is, mathematically, waves of the same wavelength but with different amplitudes and phases need to be added. The intensity of the scattered beam can be obtained by squaring the resultant amplitude. Let the direct lattice translation vector be represented by rho j equals to xj into a vector plus yj into b vector plus zj into c vector. For reflection from the HKL plane, the reciprocal lattice vector is g, which is equals to h into a vector plus k into b vector plus L into C vector. Since A dot A vector is equals to 2 pi is equal to small b vector dot capital B vector equals to small c vector dot capital C vector, therefore rho j vector dot g vector equals to 2 pi into xj into h plus yj into k plus zj into L. The resultant amplitude for a given HKL reflection or structure factor can be written as S or F equals to summation over j Fj exponential minus I rho j dot g. S or F equals to summation over j Fj exponential minus iota into 2 pi into xjh plus yjh plus zjl. Thus, the structure factor depends on the geometrical arrangements of atom in the cell. Intensity I is directly proportional to FHKL mod square, which is the atomic form factor which depends on the property of atoms located at lattice point. The structure factor need not be real. The scattered intensity I involves mod F square, that is F star F, where F star is the complex conjugate of F. If structure factor is 0, there is no intensity in a reflection G permitted by the space lattice. Thus, the structure factor can cancel some reflections allowed by the space lattice, and the missing reflections help us in the determination of structure. Now let's see the structure factor of BCC or body-centered cubic lattice. The basis of the BCC structure referred to the cubic unit cell has identical atoms at 0, 0, 0 and 1 by 2, 1 by 2, 1 by 2. That is, one atom x1 equals to y1 equal to z1 equal to 0, and for another atom x2 equals to y2 equals to z2 equals to 1 by 2. Thus, S or F HKL equals to summation over j Fj into exponential minus 2 pi I xjh plus yjk plus zjl equals to F into bracket e to the power minus 2 pi I into 0 plus e to the power minus 2 pi I h by 2 plus k by 2 plus L by 2. S or FHKL equals to F into 1 plus e to the power minus pi I h plus k plus L, where F is the scattering power or atomic form factor of an atom. The value of S is 0 when the exponential has value minus 1. The exponential has value minus 1 whenever its argument is minus pi I times an odd integer. Therefore, S is equal to 0 when h plus k plus L is an odd integer. So, there will be missing reflection. S will be equal to twice of F when h plus k plus L will be equal to even integer. So, it will be the case of allowed reflection. Let's take an example of NaCl metal which has a body-centered or BCC structure. The diffraction spectrum does not contain lines such as 100, 300, 111, 221, but it contains lines such as 200, 110 and 222 will be present. The cancellation of 100 reflection occurs in BCC lattice because the planes in Na metal are identical in composition. Therefore, alternate planes cancel the contribution, that is diffracted beam from these middle plane are out of phase by pi with respect to first plane, as the effective number of body centered atom is equal to effective number of corner atom in a BCC structure. In case of cesium chloride or CSCl, cancellation does not occur. The planes of cesium and chlorine ions are alternate, But the scattering power of cesium is much greater than the scattering power of chlorine because Cs plus has 54 electrons and Cl minus has only 18 electrons. Position of Cs is 0, 0, 0 and position of Cl is 1 by 2, 1 by 2, 1 by 2. So S will be equal to FCS into exponential minus 2 pi I into 0 plus FCl exponential into minus pi I H plus K plus L, which is equals to FCS plus FCl into e to the power minus iota e to the power minus iota pi H plus K plus L. So for this, if H plus K plus L is even, then S will be equals to FCS plus FCl into 1, that equals to FCS plus FCl. And if H plus K plus L is odd, then S will be equal to FCS minus FCl. Now let us calculate the structure factor of face-centered cubic lattice or the FCC lattice. The bases of the FCC structure refer to the usual cubic unit cell has identical atoms at 0, 0, 0, 0, 1 by 2, 1 by 2, 1 by 2, 0, 1 by 2, 1 by 2, 1 by 2, 0. Thus, SHKL equals to F into 1 plus e to the power minus iota pi K plus L plus e raised to the power minus iota pi H plus L plus e raised to the power minus iota pi H plus K. If the indices HKL are even integers, then SHKL equals to 4F. If the indices HKL are odd integers, then S equals to 4F. If 2 are odd and 1 is even, then S will be equals to 0. And if 1 is odd and 2 are even then S is equals to 0. So we conclude that no reflections can occur in a FCC lattice if the indices are partly even and partly odd. Now let us discuss experimental X-ray diffraction methods. We have already studied that diffraction can occur only when Bragg's law is satisfied. This equation applies conditions on lambda and theta for any given crystal. With monochromatic radiation, a single crystal will not produce diffracted beams for arbitrary angle of incidence of X-rays onto the crystal. In order to satisfy Bragg's law, it is necessary to scan in either wavelength or angle to satisfy diffraction conditions. Experimentally, it is done by providing a continuous range of values of either lambda or theta during experiment. The ways in which these quantities are varied distinguish three main diffraction methods. Number 1, the first method is Law's method, second method is rotating crystal method, and the third method is the powder method. You can see a compiled table below in which you can see the method along with its lambda and theta. So in the Lowe method, lambda is variable and theta is fixed. In rotating crystal method, lambda is fixed and theta is variable. And in the powder method, again lambda is fixed and theta is variable. The next method is Lowe method. In 1912, Max von Laue was the first of all who suggested the use of a crystal as a three-dimensional grating to study the nature of X-rays. Thus, the method was named as Lowe method, and it was the first method which was ever used for diffraction, and it produces von Laue's original experiment. In this method, a beam of white radiation, that is X-rays of continuous wavelength, is allowed to fall on a single crystal which is held stationary. The Bragg's angle is thus fixed on every set of planes in the crystal, and each set selects and diffracts that particular wavelength which satisfies Bragg's law for the particular values of d and theta. Each diffracted beam thus possesses a different wavelength. In this method, a source is used to produce a beam of X-rays over a wide range of wavelength varying from 0.2 angstrom to 2 angstrom. A pinhole arrangement is used to produce a well-collimated beam. The dimensions of single crystal are taken to be small, that is less than 1 millimeter. The film is flat and placed perpendicular to the incident beam to receive the diffracted beams. Depending on the relative positions of source crystal and film, the Lavey method can be carried out in two ways: transmission Lavey method and back reflection Lavey method. In transmission Lavey method, there is also the original Lavey method. The film is placed behind the crystal to record the beams diffracted in the forward direction as shown in the given figure 1a. The name transmission is derived from the fact that the diffracted beams are partially transmitted through the crystal. In the back reflection Lavey method, the film is placed between the crystal and the X-ray source. The incident beam passes through a hole in the film and the beams diffracted in the backward direction are recorded as shown in figure 1b. So in the figure 1, you can see the transmission and back reflection Lavey method. In both the cases, the diffraction pattern forms a series of spots on the film. Each reflecting plane in the crystal selects from the incident beam a wavelength satisfying Bragg's equation. The obtained pattern will give the information about the symmetry of the crystal. If a crystal having four-fold axis of symmetry is oriented with the axis placed parallel to the beam, then the law pattern will show the four-fold symmetry. This feature makes the law pattern particularly useful for checking the orientations of crystal in solid-state experiments. However, it suffers from certain disadvantages for crystal structure determination. Because of the wide range of wavelengths, it is possible for several wavelengths to reflect in different orders from a single plane, and different orders of reflection may superimpose on a single spot. This makes the determination of the reflected intensity difficult. Law method is suitable for the quick measurement of crystal orientation and symmetry. It also indicates the crystalline imperfections under mechanical and thermal treatment. The second method is the rotating crystal method. In this method, a single crystal is rotated about a fixed axis in a beam of monochromatic X-rays. The variation in the angle theta brings different atomic planes into position for reflection. A simple rotating crystal X-ray camera is shown in the given figure below. The film is mounted in a cylindrical holder concentric with a rotating spindle on which the single crystal specimen is mounted. The dimensions of the crystal should be small, generally less than 1 millimeter. The incident X-ray beam is made nearly monochromatic by a filter or by reflection from an earlier crystal. The beam is diffracted from a given crystal plane whenever, in the course of rotation, the value of theta satisfies the Bragg equation. Beams from all the planes parallel to the vertical rotation axis will lie on the horizontal plane. Planes which other orientations will reflect in layers above and below the horizontal plane. In this method, not every plane can reflect, nor could one those spacing is so small that lambda by 2d is greater than 1. The reflected spots form parallel lines. Since the wavelength is known, the spacing d may be calculated using Bragg's equation. Reflections from planes in different orientations may overlap on the film, And to make the identification of the spotless ambiguous, two modifications of the apparatus are employed. The first modification is the oscillation method and the second is the Wiesenberg method. In the oscillation method, the number of planes which can reflect is restricted by oscillating the crystal through a small angle. While in the Wiesenberg method, while the crystal rotates, the film is translated parallel to the axis of rotation, the two motions being synchronized. These two modifications are usually used in the complete crystal structure analysis. This method is best suited for the structure determination when the sample is a single crystal. It is also useful for determining the size of unit cell. The third diffraction method, which is the powder method. The method was devised by Debye and Scherer in 1916 for the determination of the structure of the small grained crystallites or finely powdered polycrystalline materials. An important use of this method is in the study of phase diagrams of alloy systems. In this method, a finely powdered specimen or a fine-grained polycrystalline specimen contained in a thin-walled capillary tube is held on a movable mount at the center of the cylindrical camera where incident monochromatic radiations strike. The distribution of crystallite orientation will be nearly continuous. The powder method is convenient because single crystals are not required. Diffracted rays go out from individual crystallites which happen to be oriented with planes making an incident angle theta with the beam satisfying the Bragg equation. Diffracted rays leave the specimen along the generators of cones concentric with the original beam. The generators make an angle 2 theta with the direction of original beam where theta is the Bragg angle. The cones intercept the film in a series of concentric rings to ensure that all possible sets of planes face the incident X-rays. The specimen is rotated slowly during exposure. Experimental arrangement of the powder method is shown in the given figure 3 on the next slide. From the Bragg equation, differentiating with respect to theta, we can obtain delta n lambda by delta theta equals to 2 delta d by delta theta into sine theta plus 2d cos theta. For monochromatic X radiations, that is with constant lambda, delta n lambda by delta theta is 0 because lambda is constant. So, delta d sine theta plus d cos theta into delta theta equals to 0. From this, we can obtain delta theta divided by delta d equals to minus tan theta divided by d. Thus, the variation in theta for small change in d is very large as theta approaches 0 degree. The reflected lines occur at 2 theta from the incident beam so that the maximum sensitivity is in the backward direction. This method can be applied to any type of material having crystalline arrangement and does not require single crystals. The given figure 3 shows the X-ray powder diffraction camera having the monochromatic beam entering through pinholes, and there is film concentrated with specimen, and in the center there is a polycrystalline specimen. So students, let us now summarize what we have learned in this module. First of all, we learned about the diffraction directions. Then we studied about the intensities of diffracted beams. Then we studied what is a structure factor or the geometrical factor, and then we explained them using examples of base cubic centered and the face centered cubic lattices. Then we studied about the experimental X-ray diffraction patterns, out of which we studied the 3 diffraction methods. First one is Love method, second is the rotating crystal method, and third one is the powder method, and these three methods we studied in detail. Thank you.